So a little bit of a difference here. We're kind of mixing it up. I'm here to introduce Mr. Marquis because he's such a celebrity now. For those of you that don't know me, my name's Ch7and8Section4, and chemistry's pretty awesome. So here is Mr. Marquis. Rock on.
That's fantastic. Thank you, Jackson. Just a little extra for your viewing pleasure. I'm sure you're going to enjoy that. Jackson, take care of yourself.
Thank you.
All right, so we're now going to, whoops.
Jesus, sorry.
That's all right. So we're now going to take a look at covalent bonding, okay, so for the sharing. And here's where we get into some of the new stuff. And I think one of the real keys is looking at Lewis dot diagrams. And what are Lewis dot diagrams? Well, they're used to show the number of valence electrons which can be used for bonding. You kind of saw me do it real quick at the beginning, but Lewis dot diagrams, it just shows you how many valence electrons used for bonding. So, something like, and again, remembering back to the fact that sodium is in group 1, family 1, the alkali metals, it has 1 valence electron. If I move right across on that family here, let's go with magnesium. Magnesium would have 2. Okay. The next, aluminum. Aluminum, 3 valence electrons. Okay, so these are our Lewis dot diagrams. Notice that I'm separating them, and again, I should be separating them because a full set of valence electrons is 8, which means if electrons can be paired, then we would have 4 sets of paired electrons. So what we're going to do is we're going to, let's say we have an atom here, we're going to have 1, 2, 3, 4 locations where we can have some pairing, some of these electrons. So we're going to separate them until we need to pair them up. So if I now move to the carbon family, 1, 2, 3, 4, so 4 valence electrons. If I now look to nitrogen, 1, 2, 3, 4, and 5. Okay, so now we have the 5th one, so it now pairs up. We've gone through our 4 locations, now we have our 5th one. So this is 1 valence electron here, all the way through 5 so far. I'll erase that, it's kind of a mess. But now let's take a look at our next one, oxygen and its family. 1, 2, 3, 4, 5, 6 valence electrons. The halogens, fluorine, 1, 2, 3, 4, 5, 6, 7. Oops, what am I doing? I'm thinking ahead here. 7 valence electrons. And of course, the noble gases have a full set, which is 8 valence electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Now the ones that are already paired, makes sense since you can have pairing due to the Pauli exclusion principle. You can have pairing as long as they're opposite spins. The ones that are already paired, let's say like nitrogen here or oxygen, these two, already paired, so therefore they cannot share if they're going to form a covalent bond. So the covalently bonded substance are going to be the ones that have single. The single dots, and our dots again are our Lewis dots, and representing electrons, are the ones that can share. Okay, they're the ones that can share, and they're the ones that are available. So for example, nitrogen has 3 available to share. 3 available to share. Fluorine and the halogens, let's get a different color here. The white would look good. Fluorine only has the 1. These are already paired, so 1 available. Now just don't get confused. There are 7 still valence electrons on fluorine, but only 1 available to pair. Okay? So that's a little description of our Lewis dots and what that does for us. Now let's take a look at
There's a student government meeting beginning right now up in the library.
the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory, VSEPR. It's used in creating all molecular structures. Allie's going to have to wait just 1 minute. So VSEPR, valence shell electron pair repulsion theory, and it's used in creating structures. What it basically says is this: electrons want to get as far apart as possible. As it says here, repulsion, electrons want to get as far from each other as possible. Okay, and it makes sense. They're all negatively charged, therefore they want to certainly get away from each other. So this VSEPR theory does that. Let me just quickly show you another example, or kind of how that works. These chlorines, if I have 2 chlorine atoms, 1, 2, 3, 4, 5, 6, 7, they both have 7 valence electrons. There we are. These will be the sharing. And there will be some repulsion here between all these electrons. And the next slide is going to really kind of talk more and more about this VSEPR, but know that that's kind of the key to all this molecular geometry and molecular structures.